Next, we want to look at phasor diagrams. One thing we wanted to make note of is that Z, and of course Y as well, that they are frequency dependent. Your function of frequency. Be very careful about that. Now, if we make a table of it, we will see, make a comparison of Z and Y. Now, for ZC and ZL, we have ZL is equal to J omega L, where ZC is equal to negative J 1 over omega C. So what we want to look at here is that if we wanted to compare the frequencies, so we imagine that we have a high frequency, where here we wanted to compare with a low frequency. And then you can see from the frequency dependence of the impedance for inductor, if the omega is high, the omega is high and this is large, the impedance of the inductor is very large for high frequency. On the other hand, if the frequency is low and the impedance of inductor is small. Similarly, if we look at the impedance of a capacitor, because the frequency is in the denominator, the higher the frequency, the smaller the impedance of this capacitor. So this becomes small in the high frequency region. Where for low frequency, the impedance of the capacitor is large. And that physically makes perfect sense. That capacitor, the current depends on the rate of change of voltage. Remember, the I is equal to C dV dt. So the more rapidly the voltage changes, the greater the current is going to be. If for a very low frequency, it's almost like changing very slowly, so the impedance is really, really high. But if the frequency changes rapidly, there's a high frequency, current is great, the impedance is really small. Now, to the extreme, often in circuits, that you have seen that in chapter 7, the transient circuits already, that for extremely low frequency, this behaves just like open. Extremely low frequency. Imagine if the frequency approaches to 0, which make it DC. Once it's charged up, there's nothing, no current can go through. So it's that infinity of the impedance. But when you look at the inductor at very low frequency, and the inductor just behaves like a wire. So the change is very small, and the induced EMF is really, really low. And so there's no induced current against the change. So it behaves like just simply a piece of wire. And so in this case, it's, again, to the extreme, it's like it behaves like a short. Now, of course, that just the opposite for high frequency. When the frequency changes really rapidly, and induced EMF is constantly there present, there's constantly induced current try to against the change. So there's a huge, high amount of impedance there. And again, to an extreme, that behaves like open, and the capacitor behaves like short if the frequency is really high. So this is the behavior of the elements in how elements in relation with the frequency. We can also examine that by looking at a circuit. That first we wanted to look at a couple of elements that we're going to have resistors, inductors, and capacitors, and make them in parallel in a very simple circuit here. So we have a current source, and we have a couple of elements here that is in parallel, and we're going to have a capacitor here and inductor here and resistor here. They're all in parallel. And what we notice here is that if they're in parallel and the current going through each of these elements, the sum is equal to the total currents that provided by the source. So we're going to call this IR. We're going to call this IL. We're going to call this IC. And we also notice that there's only this is called a single node pair. There's only one pair of nodes here. One node on the top, one node on the bottom. And so they all have the same voltage across them. So there's just a V of everyone, the same voltage. Now let's look at, by using Kirchhoff's law, that the total current comes in, KCL, is equal to I1, which is IR, plus IL plus IC. Now we wanted to express all the currents in terms of voltage because they all have the same voltage here. So we can make comparison, and IR equals V divided by R. IL is equal to V divided by ZL, which is J omega L. And then, of course, the current for the capacitor is V divided by the impedance of capacitor. That is 1 over J omega C. Now what we want to look at here is we want to look at this phase. So let's again do this here. Just do one more line here. V divided by R. And here the J is the enumerator in denominator. And so that's make it to be, if I bring it over, multiply by a J here. And here you can see we're going to bring a negative sign. J times J is equal to -1. So we're going to bring a negative sign in here, so minus or plus V here. We are going to put the negative 90 degrees in here because of the negative sign. And divide by omega L. And here we're going to have, now remember this 1 over J omega C. So bring it over, just become J omega C, where the J we're going to put into the phase angle. Now, we can draw this in phasor diagram. And we can use, because everybody share the same voltage here, we're going to just say, okay, imagine the voltage here is in here. It really doesn't matter where it is, but it's all relative, relation here. So you can see the current is in phase with the V. So this is a V, the black is a V. Current is in phase with the voltage here. So this is IR. But if you look at the IL, you notice that the IL is negative 90 degrees compared with the voltage. So the IL is here, is lagging voltage by 90 degrees. So this is IL. IC is here, because IC is leading voltage by 90 degrees. Now, whether the IC is larger or IL is larger depends on the frequency. So now let's look at for low frequency. And you can see the omega, if omega is small, and then the current here should be large, so IL is larger than IC. So clearly that situation in this here, because IC is larger than IL, that's corresponding to high frequency. So for high frequency, what do we have then? You can see the frequency is right here, and high frequency, the IL will be larger. So if we have another phasor diagram, the IL is larger, and IC is smaller. And therefore, you can see the combination of the IL and IC would be in the opposite, in the negative direction here. So this is IL minus IC, where IR is still here. Therefore, the sum of the total currents would be here. Now you can see that this time that the current is lagging is in the negative direction. So this is I, S, where IV is right here is real. Therefore, the IS, the total current, lags the voltage in this case. Now, what happens here, there's one special case which is interesting. Now, if we come here, look at the phasor again, IR is right here. Now, what happens if IL equals IC? You can see, what if my IL right here and my IC here, and they're equal? And then there's no imaginary part. There's I total would be just IR. So that would be IS. And in this case, V, the voltage of the circuits, is in phase with the current of the circuits. When does that happen? Let's look at the current here. You can see I, the V divided by omega L, that current is equal to the voltage divided by 1 over omega C. So you can see omega L has to be equal to 1 over omega C, and that is when the two currents equal. And from there, we can see that omega squared is equal to 1 over LC. Therefore, omega is 1 over square root of LC. This is what we call resonant frequency, which is the natural frequency of the circuit.